For millennia, humanity has gazed upon the moon, a silent sentinel in our night sky. Once thought to be a desolate, bone-dry sphere, recent scientific revelations are transforming our understanding of our celestial neighbor. Imagine a place where the very essence of life, water, lies hidden in vast frozen reserves, waiting to fuel humanity's greatest adventures. This isn't science fiction. It's the astonishing reality unfolding in the shadowy depths of the lunar poles, where new research suggests the moon harbors far more water ice than we ever dared to dream. These discoveries aren't just fascinating, they are a game changer, promising to unlock an era of unprecedented lunar missions, permanent outposts, and even serve as a vital stepping stone to the stars. The moon, our closest cosmic companion, has always been a symbol of exploration and aspiration. For centuries, it was largely perceived as an inert, barren rock, devoid of the dynamic processes that shape Earth. Yet, the relentless pursuit of knowledge by scientists and engineers is steadily peeling back the layers of this perception, revealing a moon far more complex and resource-rich than previously imagined. Central to this paradigm shift is the growing body of evidence confirming and expanding the presence of significant water ice deposits within the moon's polar craters. This isn't merely an academic curiosity. It represents a fundamental shift in our approach to space exploration, offering the potential for sustainable lunar living and deep space travel. Water, the universal solvent and the bedrock of all known life on Earth, holds an equally pivotal role in the vast emptiness of space. Beyond its immediate necessity for human survival, providing hydration and basic sanitation for astronauts, water possesses an extraordinary versatility critical for ambitious space endeavors. Through the process of electrolysis, water molecules can be split into their constituent elements, hydrogen and oxygen. Hydrogen, a potent propellant, can be utilized as rocket fuel, while oxygen serves as an oxidizer for that fuel and, crucially, as breathable air. The revelation of substantial water ice reserves on the moon dramatically alters the economics and logistics of space travel. It potentially eliminates the prohibitive cost and immense logistical challenge of transporting every drop of water from Earth, thus paving the way for more frequent, affordable, and ambitious missions. The journey to uncovering lunar water has been a testament to scientific perseverance, marked by incremental discoveries that collectively built an undeniable case. The first tantalizing hints emerged in the 1960s, with analyses of lunar rock samples brought back by the Apollo missions. While these early findings suggested only trace amounts of water and reinforced the notion of a generally arid moon, they sparked a debate that would simmer for decades. By the late 1990s, NASA's Lunar Prospector mission provided a stronger, albeit indirect, clue. It detected hydrogen-rich regions at the lunar poles, a compelling indicator of potential frozen water beneath the surface. The true breakthrough, however, arrived in the late 2000s. The Moon Mineralogy Mapper M3 instrument aboard India's Chandrayaan-1 mission, along with the High-Resolution Infrared Spectrometer HRI on NASA's Deep Impact spacecraft, directly confirmed the presence of widespread, albeit thin, layers of water and hydroxyl, a component of the water molecule, across the lunar surface. These findings conclusively demonstrated that the moon was not entirely bone dry. A small but significant amount of water existed, albeit in a diffuse form. But the most dramatic and unequivocal evidence came in 2009 with NASA's Lunar Crater Observation and Sensing Satellite, LCROSS mission. In a bold experiment, LCROSS was deliberately guided to impact the Cabeus crater near the moon's south pole. The resulting plume of ejected dust and vapor was meticulously analyzed by spectrometers, which definitively confirmed the presence of substantial quantities of water ice. This groundbreaking experiment provided concrete proof that the permanently shadowed regions, PSRs, within the lunar polar craters, areas that have not seen direct sunlight for billions of years, act as cold traps, perfectly preserving water ice. More recent investigations are now expanding on these foundational discoveries, suggesting that the volume of water ice within these cold traps may be far greater than initially estimated. These new insights stem from sophisticated analyses of data collected by various lunar orbiters, such as NASA's Lunar Reconnaissance Orbiter, LRO, employing advanced modeling techniques and enhanced data processing. Firstly, it's increasingly believed that the ice isn't just a superficial layer. Instead, it might be interspersed within the lunar regolith, the moon's pulverized soil, beneath the surface. Radar and neutron spectrometer data consistently show higher than expected hydrogen levels within the regolith, hinting at buried pockets of ice. This implies a more widespread distribution rather than just isolated surface deposits. Secondly, detailed thermal models and topographical analyses of the craters are revealing that the permanently shadowed regions themselves might be more extensive than previously mapped. Due to the moon's axial tilt and orbital characteristics, the bottoms of some deep polar craters remain perpetually shielded from sunlight, with temperatures plummeting to below 200 degrees Celsius, 328 Fahrenheit. These extreme cryogenic conditions are ideal for trapping and preserving water ice molecules, preventing them from sublimating into space over geological timescales. Thirdly, some research suggests that in addition to water brought by comets and asteroids impacting the moon, in situ water production mechanisms may also contribute to the lunar water inventory. Hydrogen ions from the solar wind reacting with oxygen in the lunar soil can form water. These localized production processes could help continuously replenish ice reservoirs, making them a more dynamic and renewable resource than previously thought. The burgeoning potential of lunar water ice is a revolutionary prospect for future human missions, especially for programs like NASA's Artemis. Both NASA and its international partners aim to land humans near the moon's south pole by the late 2020s. This region is a prime target, not only for its fascinating geological formations offering immense scientific discovery, but crucially, for its proximity to these vital water ice reserves. Establishing a permanent lunar base presents enormous challenges, particularly regarding the sustainable provision of life support and propellant from Earth. Lunar water ice offers a transformative solution to these hurdles. Potable water and life support. Once extracted and purified, lunar water ice can supply astronauts with drinking water, water for hygiene, and other domestic needs. This drastically reduces the need to launch heavy water payloads from Earth, freeing up valuable cargo space. Breathable air. Oxygen generated through the electrolysis of water can replenish the breathable atmosphere within closed-loop life support systems at a lunar base. This is a critical step towards creating self-sufficient lunar habitats. Rocket propellant. Hydrogen and oxygen can be recombined to form powerful rocket fuels. Made on the moon propellant is absolutely vital for spacecraft launching from the lunar surface or refueling in lunar orbit. This would transform the moon into a pivotal staging post for deep space missions to Mars and beyond. Considering the immense amount of fuel required to escape Earth's gravity well, producing fuel on the moon would dramatically cut the cost and complexity of interplanetary travel. Radiation shielding. Water is an effective shield against harmful space radiation. Integrating water storage tanks into the outer walls of lunar habitats could provide an additional layer of protection for astronauts and sensitive equipment against the harsh radiation environment of space. While the presence of lunar water ice is incredibly exciting, extracting and processing it presents a formidable set of engineering and technical challenges. Overcoming these hurdles will require ingenuity and significant technological advancements. Extreme cold environment. The temperatures within permanently shadowed craters are brutally cold, posing a significant risk of equipment freezing and malfunctioning. Robust robotic systems and advanced heating mechanisms that can operate reliably in these cryogenic conditions must be developed. Abrasive regolith. The fine abrasive lunar dust, or regolith, is a notorious threat to mechanical systems. Its sharp electrostatic particles can degrade seals, abrade moving parts, and contaminate sensitive instruments. Power source. Operating in regions devoid of sunlight necessitates a reliable and substantial power source. This could involve long-distance power transmission from sunlit areas, deploying mobile nuclear fission power units, or utilizing innovative mirror systems to direct sunlight into the shadowed craters. Extraction and purification technologies. Various methods for ice extraction are being explored, including excavation, thermal heating, or microwave processing. Once extracted, The raw ice will need to pass through sophisticated purification systems to remove harmful contaminants and render it suitable for drinking or converting into rocket propellant. The promise of lunar water ice extends beyond national boundaries, fostering an environment ripe for international collaboration and even the emergence of a future lunar economy. International agreements will be crucial to ensure the equitable and sustainable utilization of these invaluable resources. Private companies are also keenly aware of the potential for lunar resource extraction and commercialization, heralding the dawn of a new era in the space industry, one where the moon is not just a destination but a vital supplier. The discovery of lunar water ice has transcended mere scientific curiosity. It has become a tangible, strategic asset for humanity's future in space. Its presence and potential utilization represent a critical step toward establishing a sustained human presence on the moon, deepening scientific research, and ultimately realizing our ambitious goal of reaching other planets within our solar system. The white gold hidden within the moon's dark, frigid craters is poised to become the propellant for humanity's next great leap into the cosmos. Future lunar missions will undoubtedly focus on exploring, extracting, and harnessing this precious resource, transforming the moon into an indispensable forward operating base for our journey among the stars.